Okay, real quick, I just wanted to remind you, I hope since your freshman year, 4 years ago or further, you remember some things about the H atom, how you have a principal quantum number, which we now know is the row of a periodic table, SPD, and of course there's only one S, there's 3 Ps and 5 Ds, and we won't worry about Fs. There's a reason they're in their own block. So I just want you to remember that. Now we're doing the two-dimensional, we're doing three-dimensional today. And the particle in a sphere is not the hydrogen atom because it's the same except for the Coulomb potential. But it has a lot in common. Now don't try to memorize this. Now I hope if you have a PhD, you ought to know this no matter what. But there's some differences between particle and a sphere, or we're doing particle and a ring. Particle and a sphere is today in hydrogen atom. I just want to point that out. It's just kind of interesting, but you don't need to memorize this kind of stuff.
Question.
What?
Right. So as a number, isn't n a natural number for like 1, 2, and 3? Like L is n-1?
Oh, right. I was just copying L. Right. N of 1. L is 0. Yeah, thanks for pointing that out. Right. Row 1, 2, 3. There's no row 0. Yeah, thanks for pointing that out. And L, I forgot the rule for N and L.
L is n-1.
Is what again?
And L is up to n-1.
Up to n minus 1.
0 to n-1.
Yeah, right. Yeah, 0 to n minus 1. And of course, m sub L is minus L plus 1. And that comes about from when you solve the Schrodinger equation. Actually, you got to delete that from the video. That's embarrassing. So anyway, I forgot what I lost my train of thought. It's okay. All right. So remember, this is the radial part of the 2D particle in a sphere. The angular part is manifesting itself right here. And we know that m sub L is a whole number. And the solution, and this is to answer one of your questions. Notice I was answering one of your questions last night. Sorry, last time I was that one idiot. That you have different orders. And here I'm drawing 2. Okay, and this is J0, and that would be like an S-like. And you may recall from I showed some wave functions last time. So the J0 is the drum when it's just vibrating. J1 is one with a node in it, a single node. So you can imagine a drum surface might start doing that. And I showed you some MATLABs the other day. Notice that, again, what's kind of funky about this is that there's natural crossing points. There's natural crossing points for these that occur at certain values that are not sensitive to what the function is being applied towards. So these numbers don't change depending on what your model is. So Bessel functions are the solution to a bunch of stuff, let alone particle in a ring. Right? So these are Bessel functions. When we do spherical, which we're doing today, those are spherical Bessel functions. These are Bessel functions, and then there are spherical Bessel functions that are not the same. Okay, just want to make sure you know that. Okay. Now, analogous to a 1S, now that you see these, the way this works is, this is basically a, how do I want to put this? This is the 1S. Okay, and the, basically this being the wave function, the radial wave function, it needs to end at A, right? Where A is the radius. Well, sorry, now remember that there's really like 2 radiuses. The particle is not on a string. The particle is anywhere inside of this ring. So the distance to the origin is R. But when the particle gets as far as A, when R equals A, then it hits an infinite wall. So now remember, you should have done particle in a string in your undergrad. It's in my little textbook. The radius doesn't change. It's stuck on the edge of the track. But here the particle can be anywhere inside. This is why this is a grad school problem, not an undergrad problem. Okay, now, so there's a nice analogy between here and here. Okay, but now here's where there's a slight difference. There's actually another zero. There's another zero. And this whole thing is now that I've let it go, now that it has a node, this is a 2s. Right? So that's how that works. And it ends, now the end, this still ends at A. Anyway, okay, so now let's look at the T state, and this ends at 3.83. So this is now here again we see a difference. There's no such thing as a 1p state for the hydrogen atom, but there is a 1p state for a particle in the sphere. That's a 1p. Now again, a 1p does not exist for a hydrogen atom. There's only a 2p. Now a particle in the sphere does also have a 2p. That's the 2p state. Anyway, I just want to make sure that, you often see this type of electronic structure applied to nanoparticles. That's where it's different. So people make a lot of mistakes when it comes to nanoparticles. They mention that they have hydrogen-like electronic structure. That's actually wrong. That is a common misconception. They have particle in a sphere electronic structure, not hydrogen atom structure. It's a very big mistake that keeps getting propagated, and it's wrong. Particle in a sphere. Okay, and now recall also that I mentioned to you that the way that this sucker ends up getting solved, you don't really end up with the function as a function of R, it ends up being KR, where your K is hiding right here, right? So because of that constant right there, I have to admit, I don't quite remember how this works out, but for the particle in the sphere, the argument ends up not being R, it ends up being KR. And it has to be this way because K is 1/meter and R is a meter. And you need to feed this thing something without units. And it also, to answer your problem, I said this last time, to solve for the 1s state energy, K is your energy, that's what your unknown is. Now R, when R is equal to A, you better be 0. Right? That's the boundary condition. That's how you apply the boundary condition, right? Remember, this is one of the ones you find the function, which is J, and you apply the boundary condition, which you're seeing right now. Now that means that this thing has to be 2.4 equals Ka, where K as always is 2me. There's no potential energy because you don't allow it to have a potential energy because it's infinite. There you go. And so now you solve for energy. And that's how you do that problem. Now, again, if I was asking you for the 1p state, you would just put in 3.83 for there. I could ask you about a 2s state, wherever that number is, it's like 4 point something. That's also probably like 5. Anyway, so that's how you do it. Now, heads up, I'm making this look easy. When you actually do this, you're going to get confused. It's just the nature of the beast. Also, I want to point out that those are the radial. Remember that the full wave function would be J of, well, okay, so let's do S state. So say it's a 1S. Oh, no, I need to do sorry. So that's a 1S, but let's do a P state. So you'd have two different, remember I showed you last time, if the drum has a node, there's actually two of them. one where it's turned this way and another one where it's turned that way. And that's what you're seeing, this behavior here. Note that because linear combinations of wave functions are legit wave functions, the way we often express this is this way. And so instead of two that look like this, and again, I'm talking about p states, for an S state, remember n sub L is 0, so that there is no factor there. There is no angular part. Okay, so because linear combinations of real wave functions are also real wave functions, real meaning legit, what we like to do is when we have these angle parts, we like to do linear combinations, because what this allows you to do is it allows you to get rid of the imaginary component. So we call that cosine and that's sine. So I would call that x and y. So that's like a px and a py state. Now I know that there's technically an imaginary number. Sine is really I sine, but again, the normalization constant chews it up. If you want to be a math stickler and say that's really 2I sine, when you solve the normalization constant, it'll also have an I in it, and it'll destroy it. So I'm never worried about little factors of 2 or even I, because quantum mechanics has a way of getting rid of it. So another thing to note is that this is a traveling wave. The reason that we do this is, for one, to simply get rid of the imaginary functions, especially for undergrad level stuff. But there's also another reason, which is that over time, the way that e to the I phi works is that the waves in time are going this way. But what happens here is this. Okay, so this is increasing time, and it looks like it's going that way. This is increasing time, and they're dog patterns, just doing this. One isn't right, or it's not like, oh, that's wrong, that's right. No, they're both right. It's just how do you want to think about it? One of the things about these stationary waves is that people like them, is because we don't like to think of the electron as like really if this is an electron, we don't like to think of it as rotating because it ought to be shooting out electromagnetic radiation. So for those of you who hopefully you've heard this before, but Bohr had a model for the atom. Bohr's model of the atom got the energies right, and everyone was very excited. But even for the S state, the electron rotates about the nucleus. And it should be a radio transmitter. If it's rotating, it's transmitting light. All electrons in circular orbits generate photons. So why doesn't Bohr's hydrogen atom? Well, it's because his model is wrong. It turns out that when you make linear combinations, it's a standing wave, it's not moving. It has rotational energy, but not rotating. I mean, and you're like, oh, that's not possible. Well, that's quantum, and that's why this stuff is kind of a pain. But when Schrodinger was able to show, like, okay, I can get the same energies, and I have a model that technically doesn't have the electron necessarily rotating, even though it has rotational kinetic energy, that resolved the problem, and everyone accepted the solution. Okay, anyway. All right, 3D. 3D particle in the sphere. I kept saying particle in the sphere. We're doing particle in the ring. Now we're doing particle in the sphere. X is R, and you may notice that I am not having you solve the kinetic energy operator in 3D. I started on it once, and I saw that it's going to be 20 pages of algebra. I mean, hopefully that problem you're doing, it's not that bad, right? Because I'm walking through it in parts. If you had to do 3D, use the trig to convert to 3D. That would just be, I mean, obviously it's doable. It's just pages and pages and pages. And that's manifest in the fact that, you know, the 2D cylindrical kinetic energy operator wasn't that bad, right? I mean, it starts out bad. There's like 16 terms that you're working on, but it collapses into a nice simple form. Yeah, that's not happening here. This is not easy, unfortunately. Gotta love this. Now remember, this is still, oh, yeah, that's right. This is still dx squared, dy squared, dz squared. That is fundamentally what this is. It's just converting it into rotational this and that. Makes it hideously complicated. Yeah, it really wasn't that bad in 2D. In 3D, holy God. So there you go. Now I hope you can accept the fact that you know you can do this. You can do that problem I have in your homework. You can do it through me. You can do it. It's no dangerous, but you can do it. So let's not worry about it. Okay, we're going to do 3 particle in a sphere. So as usual, and the last time we're going to do this, right? We're going to flat potential energy, so we're going to make that go away. But just like the particle in a ring, we're then going to apply them later. So again, this is actually the abnormal way to approach these problems. You won't see this happen again. This is the last time you'll see this. Solving wave functions and then boundary conditions. It really does not work that way. Okay, so we're not going to have any potential energy. We'll use it later. And then here's another thing we're going to do. Now remember that you separate wave functions at the beginning. Separable. R, theta, bad, not separated. R, theta, phi, triple bad, not separated. Not separable solution. Okay, now the idea again is that it is separable, we just don't see it yet. So here's how we're going to do this. We're going to use a trial wave function. Now I hope you read, I know my little chapter on rotational quantum, the undergrad thing. It's not great, that's my very first draft, but those are spherical harmonics, so my little textbook walks you through that. And I'll show you a little bit about how it's solved, but those are spherical harmonics. Now these are separable. This is e to the, it's like, it looks like this, cosine. This is what they look like. Sine, cos, e to the plus minus I phi. It's not, and these are separable too. Okay, so that's our trial solution. Now I'm going to do that. Okay, now this is something that is very frequently done. It gets really confusing. It's just a bookkeeping. I mean, in honesty, if you've done this enough times, this really isn't hard at all. It's just overwhelming. And overwhelming is a kind of hard. This does not help. What am I dividing by R? Okay, big picture, here's how this works. I am doing this because it's going to make everything easier. But clearly it's affecting the solution. Okay, what I'm going to end up doing is, I mean, R is R. There's nothing to solve for. It's an is. But R, the function R of R, that's what I'm solving for. Okay, so this is all I'm going to plug this in. It's going to simple. The reason I'm doing this is that it's going to make it way easier. I'm going to solve for R of R, the radial function. But the real wave function is whatever I get divided by R. So that's the big picture. I'm complicating it now. because it actually simplifies it, but then it recomplicates it because I got to remember to divide by r when I get my final result. So that's what's happening. Now the reason that you do that is so we apply. What happens is it ends up looking like this. This ends up being. I'm not going to write the whole thing out. Okay, so what happens is, if I use a form of a function over r, this part here turns into 1 over r d double derivative r. Right, so that's kind of awesome. This is a little on the complicated side. I mean, the whole thing's complicated. But by applying this and doing your product rules, it turns into this. Okay, so that's a win. Okay, now I'm going to have to actually wipe this out because I'm going to rewrite it. Sorry, we need to be in a bigger room. I forgot to ask Jim to put this in a bigger room, so sorry about this. I'm going to rewrite this, but I'm going to include the wave function. And also I'm going to multiply, as you almost always see, I'm going to multiply by minus 2m over h bar squared. And r to the 3, that's new, and of course I'm also, you divide out the, sorry, I never do that the same way, it doesn't mean that. Okay, so again, big picture is doing this part simplifies when you act on the right, and then I'm going to multiply this on the left. All right, I won't wipe out the whole thing here. So normally I'd want to just toss this up so you can just kind of keep, so you can see what's happening. We definitely need to be in a different room. This is kind of ridiculous. Okay, so what you end up with is r squared. Here's a radial bit. Let's make sure it makes sense. R cubed, all right, that's on the left. And I have this 1 over r, and so I have an r squared. Right? So everything makes sense. The spherical harmonics go through these operators. So there's a spherical harmonic on top, spherical harmonic on bottom, so it's not there. Okay, so that makes sense. And of course, the reason that the radial is still on the left is because it's trapped. Because when we acted on the right, it got trapped by that. Okay. Now, the energy, which is gone, is now part of the radial because it gets multiplied by that. So we should have a 2m over h bar squared because we multiplied the energy by 2m over h bar squared. There's the energy. And you know, I'm gonna include the potential just in case. Just in case. It's not really there, but I'll keep it there just in case. And r squared. Now I know I multiplied by r cubed, but that maybe it's a mistake. Let me double check. Is that now that's an r squared. Where did my 1 over r go? I feel like I'm missing a 1 over r. Yeah, multiplied by r cubed, but it's an r squared.
That should be r. No.
It looks like I've lost a factor of r. Okay, hold on. I'll work on that. We'll figure it out. Okay. Now, the angle bits are the same deal. Let's see. I'm going to bring these over to the right so I have a minus sign. And I'm dividing out on the left. Now the one over the radial part is wiped out because the radial part was wiped out because it doesn't get trapped. It does not get trapped by all these operators if you're about to see here. I have to be careful because I see I'm running out of room. I will just be able to finish this. Okay. Actually, where did my R cube go? Okay, so sorry about this. I am kind of messing up. But so remember, we had a bunch of stuff, and I multiplied. All right. Okay. So you know these are operators. So when I multiplied by two H bars, where is it? So it's minus, but I brought it over to the left, so it's plus 2m over h bar squared, and r cubed over r is r squared. Okay, so that makes sense. I freaked out there a little bit about why that looks that way. So sorry about that. It just didn't look right. Okay. So now what? Yeah, this is awful. Okay. Number one, it's separated. So all data in theta. And these are, of course, are all r's. Okay, so I managed to separate the radial from the angles. Now the next part is if you assume that the phi is e to the minus, sorry about this, m sub l, what am I just I? Okay, like last time, we're gonna try to solve this first. And like we did on the radial part, the cylindrical is the part on the ring. We're just gonna say that we know what the phi is. And then we're gonna solve everything else and get some answers and test the answers pass. So remember one thing about quantum is there are multiple answers to this, but many of them are unphysical. So there's actually, if you start Googling Bessel functions, be careful. There's actually two forms of Bessel functions. There's actually, for all we're doing, ring, sphere, there's actually two sets of solutions. I'm not showing both of them because one of them ends up being unphysical. It just is physically, its description is physically impossible, so we're just not working with that one. So we have multiple solutions, this is one of them, but as we work the problem, it's the only one that gives the right answer. Anything reasonable. Any other thing we add here is unreasonable. Again, that's why I don't kind of like quantum so much. It's like mathematically half-assed sometimes. Okay, now, when you do that, solutions are what I've already called them. I've already called them this. The spherical harmonics. Okay, so now recall when we did the particle in a ring, I simply, there's only one angle. And so when I did this, we were done. In 3D, I'm still stipulating this, but I have a theta part. And what I stipulate here is that Well, I'm just going to go look at an 18th century math textbook because it was solved back in the 18th century. This was solved in 17 something or 18 something. Why? I don't know, but it was solved. Okay, so while that is that, the interesting part, of course, is the theta part. And this is what it looks like. And don't let it blow your head off. So you're seeing L, right? So SPD, 2L plus 1, depending on what wave function you're trying to solve. A 4 pi is a 4 pi. We get some funkiness. You know, you don't really need to write this down, by the way. Don't even worry about this. You can just Google this. Wikipedia shows you all this. Those are factorials. L minus the absolute value of m factorial over L plus the absolute value of m factorial. Okay, the only thing that might be new to you is this P thing. God, this is kind of a nightmare, isn't it? Okay, this is called a Legendre. That's a Legendre polynomial. It depends on L. So for an L of 0, an S state, the Legendre polynomial is 1. Right? So you couldn't get more simple. If L is 1, then it ends up being cos. For L of 2, it's 3 cos squared minus 1 over 2. Anyway, I've seen enough of them, I kind of have memorized. Anyway, just look it up, right? Again, solved, 17th century. There's that. And the theta part is, yeah, a little bit, but whatever. You just look it up. Okay. Now here's the thing. When you plug this in, let me write out the formula. I'm going to write out the whole damn thing again. If you look up at how you solve this, by the way, you will see that it is separated. You do have to separate the damn thing. And again, the phi part is e to the I m phi, leaving behind the theta part. And yeah, anyway. And so the end result here is what I'm showing you. And why I'm doing this will make sense in a second. Okay. All right, so I'm just writing all this up here again. Remember, we're still in this separable. We're still doing this whole separability thing, right? So act on the right by the wave function, act on the right, divide up by the left. So that's what you're still seeing. It gives you a form that is solvable by standard PyTQ. 17th century was not great. Okay, notice that what I've done here is I'm acting on the right. I'm acting on the right and dividing out on the left, which is how I just noticed that I'm missing a bracket. Notice that? How can I, yeah, you see why? There should be there too. Minus, because I moved it over to the right. Okay. Now, this should be a constant. Remember that in the separable form, you should have constant minus constant equals 0. I shifted this one over to the left, to the right for a reason you didn't see. Okay. L times L plus 1. L is a quantum number. It's a constant. Okay. In the solution, you find an infinite number of answers. Ground states and excited states. There's an infinite number of excited states. The ground state has an L of 0, and what happens is that Simon Laplace, who solved this, found this relationship and found that L of 0 is a ground state, and then you have an infinite number of excited states, which we know is S, P, D, F, G. So there you go. So the guy solving it, it's just he finds an infinite number of solutions. But they make sense to us as chemists because one's a ground state and the others are excited state. So there you go. That's spherical harmonics. Solution to this, infinite number, but that happens every time. And in the separable form, it is a constant. So again, I hope that's not going to knock your head off, but there you go. Okay, now if you all got this down because I have to erase it. Okay? All right, now the reason I have to erase it, now you see why. You remember I kept brain on and on, you have to move everything to the left instead of equal to 0 because that's what you find in math textbooks. The reason I did that was because I wanted to do this. I wanted to just take a slightly different approach. There you go. So this is what Bessel had to solve. The R part, constant. It's equal to a constant. Now you solve that. And Bessel did. Okay. Let's see. As usual, we're going to call K K squared root of 2m E over h bar squared. I know I've been kind of loosey-goosey with. No, tell you what. Yeah, I'll keep potential energy. If I keep potential energy separate from E, I can just say that's K and still keep my potential energy. I know I'm kind of playing games with the definition. Let's see here. What do I want to do? Okay, so I'm also going to divide. All right, so what do I end up with? So I'm largely just rewriting this again. E squared he's a little cat. Okay, the R's get wiped out. Now I'm going to bring this to the other side. And divided by R squared. That's divided by R squared. So 0. Now what I'm going to do is, now remember, you may have noticed I was missing this 1 over the function in the separable form. All right, one reason you do this is to get this in a Diffie-Q form that's solvable. Now 0 times R of R is still 0. Right, so that doesn't do it. Okay, so there you go. Okay, so call that K. The 2m over h bar squared is still there because for the r squared over r, I've actually multiplied through by a function of r over r squared. There's function of r over r squared. I just factored it. I brought it over, so there's a minus. 0 times anything is 0. All right, so y'all see. Again, I know that this is overwhelming. When I'm doing this, I just want to point out that there's nothing I can't point to that doesn't make sense. Everything's right. You know, if there's a 2 or a minus sign, I've screwed up. If anything isn't right, anything isn't right. And that sucks, but they pay me a lot. So that's cool. All right. So there you go. This, we're not getting out of class yet. This is the Diffie-Q to be solved. And Bessel did it. So Laplace did the angle parts in 1862 or 1863. Bessel did this, I don't know when. Of course, didn't do quantum mechanics. I'm sure, I think it was like a fluid mechanics problem that he was working on, or something like that. So they knew about fluid mechanics back then. And sometimes they just did math for math's sake. But these equations, these Schrödinger-like equations, they show up in a bunch of stuff. They're not obviously quantum mechanics, but there was a reason why people solved things that looked exactly like this. Okay, now, particle in a sphere. So I kind of screwed up earlier when I said we'll just get rid of the potential. That was enough of me. Okay, if the radius is equal to A, I'll try to 3D it a little bit. It's in a medium of, God, that was awesome. The potential energy outside the sphere is infinite. It bothers me, it's not all symmetric. Anyway, okay. So there's a sphere. You can be anywhere inside. It's not caught on a string. You can be anywhere inside. But if it goes further out than the letter A is the ultimate radius, then it's an infinite potential energy. So that's the idea. And if you don't mind if I get rid of that, this is kind of a simple way. I've been saying this over and over again. Hopefully you already do that. Okay, now check this out. If D equals 0, so now we are going to just assume that we're doing flat potential surface. And we're going to start with L equals 0. So recall that Bessel has to solve every Diffie cube for every different value of L. They ran into the same problem with the particle in a ring. We had nth of L. Every nth of L required a different solution. Here, every L required a different solution. That sucks. But that's why that guy got paid a lot of money, right? Okay. If so, what you get is this. Hey, yeah, that's kind of cool. What's the solution to that? What do you think is a reasonable solution? Delta derivative of a function is equal to itself times a constant. You've seen it before. I can't even do it. Sine, or give me something a bit more sophisticated. E to the, right, E IKR. E to the IKR. But like last time, that's like moving out from the center, that's moving in towards the center. It's moving around, half the time it's moving towards the center, half the time it's moving away. That's as legit an answer as this. Let's not forget that. Always got to have A's and B's. Okay, now, let's see here. Now there's a bit of an issue. Is this the same as the wave function? Earlier, what do you do? Divide by R. Remember? I said that the wave function was equal to R over little r. That means that while, you see why I did that, because this was very easy to solve. But R is not the wave function. R over R. R over R is the wave function. Remember, this is not the actual solution. This was part of the solution, where the other part was 1 over R. Okay, last bit and we're done. That means it now looks like Sorry, I got a little blank here. So that means, so you have to have this behavior. The wave function has to be 0 at r equals 0. If not, it'll go to infinity. Right, now you see that? So actually you can say this. You can say that the rate, that the r part has to be 0 at r equals 0. Otherwise, the wave function goes to infinity. Now, do you see that? R over r is the wave function. So if r is 0, this top part better be 0, because otherwise you got a major problem. You got an infinite wall. Okay. That means it actually has to look something like that. Okay, if that's the case, what's the relationship between A and B? A plus B is equal to 0. And now the wave function is what? A minus B. So R is really, if it's E I plus E minus I, it's cosine. It's E to the I minus E to the minus I, it's what? Sine. And there's a normalization constant, but that's it. Okay, that's classic equation.